to introduce N.Litvak from Twente, University from Netherlands, and from Russia as well, in fact. So she will speak about what about degree dependencies in random graphs with heavy-tailed degrees. Okay, I am happy to see all of you here.
Thank you. Thank you, Andrei. It's not my first time here. I have actually presented, I think, 2 years ago in the same audience, in the same room, but I guess with different people and different topic. This topic that I chose to talk to you about today is actually something that I have been working on also for a while. And I will tell some results which are old results and some which are new results. But since I think all of you, I guess, even are students, right? So I will try not to do too fast, and it's already evening and you probably are tired. So just let's try to make it fun, and I hope you'll just understand what I'm talking about now. So these are examples of networks, and these networks are very different. So this is a sample of internet. It is so-called Abelian network. It was academic network, and it's recognized as a structure which is very similar to a global internet. I don't have an internet connection here, otherwise I could show you. Did you ever see this Opta project? A picture of internet? No? Yes? You saw it. Yeah, so those who know it shared with us. It's really beautiful. So the plot of the complete internet, and this is just a sample. So those who saw this Opta picture can say that it's indeed the structure-wise resampling a little bit. And this is a network of bank transactions. And what we notice is that actually in both of these networks we have these big hubs. So the hubs are nodes with a lot of connections, with unusually many connections. So here we see these big banks, and I think here the thickness means the number of transactions. And actually these are only the most important banks here. So those in the middle of the network, they all are connected to each other. All big banks are connected to each other with some transactions. And if you look at the internet sample, then you see that actually these big hubs are not in the middle of the network. They are some of periphery. You can see, think of them as some servers which are connected to many computers, but this backbone in the middle are actually nodes of not very high degrees, but they form a very dense mesh, so that there is always alternative route for the data to pass. So when you look at these two networks, you immediately can see that they are very different. But the question is, how can we characterize this difference between these networks? And one of the things that we can think of is, just one sec, yeah, is this. So this is called degree dependencies, or degree correlations. So look at first at this picture. So here we have a node I, or vertex I, and here we have vertex J, and they're connected by an H. And what we want to know, if this I is a big guy, will he usually be connected to also another big one, or not? So we actually want to know what are the dependencies between neighboring nodes. So if nodes are connected by the H, what are the dependency between degree on the left and degree on the right? So this is a very big formula, but actually this is a very simple formula. It's nothing else but, in fact, the graph version of the Pearson's correlation coefficient. You can recognize it very easily. If you studied your probability reasonably well, then you know what Pearson correlation coefficient is. This is between random variables x and y. This is expectation of xy minus expectation x, expectation y, and divided by a square root of variance x, the square root of variance y. And that's exactly what this coefficient is. So this is classics. This is what you study in your very first probability course, maybe on your like third lecture or something, right? So this is really something elementary that we understand very well. And this is nothing else but just the same thing. So what happens here? So first of all, we are going over all ages ij, or VW, whatever you want to call them, right? So we are going to over all the ages VW, and what is this? Is it just a product of the degrees on the left and on the right? So you can see it as a product of x, y. And what we do, we sum over all possible ages, and we divide by the number of ages. So this is a so what is a prime here is that we have actually a undirected graph. I will show you. So we have the graph, and graph consists of vertices and edges, right? And it is undirected. So we have two vertices connected by an edge. So this is like V and W, and they're connected by an edge, okay? But actually, so this is in E. But what will happen in E prime, then we will replace all these edges by two edges, from V to W and from W to V. Why it is convenient, even in undirected setting, to replace each undirected edge with two directed edges? Because at some point you want to make calculations, and you want your objects to be very well defined. So when you write this VW, and when your order is not important, then some objects in your calculations are not very well defined, basically. So, but here this is very unambiguous, because it's either from V to W or from W to V. So this is a vector which is well defined. The first coordinate, the second coordinate. And here, if you want to consider this H, then this is a set. And then a lot of calculations become now a little bit more confusing. I mean, of course, you can do it both ways, but it is simply easier to do it this way, simply more convenient. That's it. So, so E prime is actually the set of edges where all undirected edges converted into directed edges, yeah. But actually, this is exactly the same thing. So we have here the product. So as here, so this is average of the product, so expectation of the product, and what we subtract is product of expectations, except of course, when we take a random H, then on the left and on the right, we will have exactly the same distribution, right? So that's why average will be the same. So instead of average x, average y, think about it that x and y have the same average, so it will be average x squared, right? And this is exactly what is written here. So this is just a random H chosen. So it is degree on the left, and on the right is just, we take just an average of this. And this will be an average of a degree on one side of a randomly chosen connection. And we take an average of that, and we take it squared. So it's exactly this term when x and y have the same expectation. And exactly same is below. So again, I can lose the square root, because variance of x, variance of y in my case is the same, because it's a random H, and degree on the left and on the right has exactly the same distribution. So what is variance? How you compute variance? Again, your first lecture in probability. For any random variable, is variance x is expectation of x squared minus expectation x squared. Right, and this is exactly what's written here. So this is just expectation of the degree squared on the two edges, on the two ends. So it can be left end or right end, and with probability 1/2. And the same is here. So this is just the same expectation squared as was here. It's exactly the same term. So all long explanation, just with one goal to show to you that no cheating here is going on. We just take the correlation coefficient as it is, and we translate it to the graph setting as precisely as possible. And then this is a big formula that we obtained, but it's not very scary, it's very easy to compute, etc. Okay, so now, are we done? As far as physicists are concerned, we are done. I mean, here is your correlation measure. And now what happens that if you have it positive, it means there are positive correlations, meaning bigger vertices tend to connect to vertices of larger degree. And if it is a negative, then it means that there is so-called disassortativity. So like bigger vertices tend to connect to vertices with smaller degrees. Right? So positive or negative, so it's called assortativity. So the network is assortative when there are positive correlations and disassortative if there are negative correlations. Fine. So Newman wrote 2 papers on it. Both had thousands of citations. And here he computed correlation coefficients for many different networks. In particular, there were social networks, technological networks, biological networks. Yeah, of course, I probably should have spent a little bit more time on motivating networks in general, but of course, you have plenty of examples, like, for example, co-authorship network, who has collaborated paper with whom, is one social network, but you also have Twitter as directed social network, Facebook as undirected social network. But here these are different. So this is email connection network and co-authorship in mathematics. And here are power grids, internet, World Wide Web, all are networks. So, and he made samples, he took samples, like this is really a very small sample of the World Wide Web. I mean, it is 200,000 or 250,000, but at the moment, World Wide Web probably has more than 100 billion indexed pages. So this is actually small. In fact, you know, it's very funny. So once I participate in program committees and computer science conferences, and in one conference there was an instruction pushed to program committee members for referring the papers, and it was saying that any experiment on the World Wide Web crawl of less than 100 million pages should not be considered seriously. So that means that this sample by no means is large. And there are also biological, for example, metabolical network means basically who eats whom. Like when you take all the species and put an arrow from a fox to a bird, if a fox eats a bird, right? But you don't put an arrow the other way. So he did all these calculations. And here are the results, and he made the conclusion that the social networks have positive, so assortative, so popular people tend to be friends with popular people, and technological, biological networks tend to be disassortative, like sort of a fox will eat birds and frogs and mice, but will not eat a wolf or any other predator. So. Anyway, so as a mathematician, then you look at this, then you may say, that's fine, but something a little bit fishy is going on here, because when the network is a little bit bigger, we actually don't observe, to begin with, we don't observe very big negative correlations. Positive correlations that we observe are usually somewhat larger than negative ones. Besides, in really big networks, you don't have. I mean, here this is his biggest sample, and this coefficient is kind of small, you know. And actually, if you look at this formula as a mathematician, then you can say, okay, my graph is my data. This is the data of endpoints, right? And I want to compute something on that data. So whatever formula I write, even before I have the graph, this is nothing else but my statistical estimator, right? This is my statistical estimator. Now, $1 million question, what do we want, the very first property that we want to see in statistical estimator? What is the main thing that we want? Statistics. Huh? Yeah, unbiasedness is good, but for unbiasedness you have to take an expectation of this whole bloody thing. There is something in the numerator that will be a little bit tricky, but yes, it's a desirable property. But even before unbiasedness, what we want from estimator is so-called consistency. And what consistency means is that your estimator, actually when your sample size grows, then your estimator converges somewhere and preferably converging to the right value of the parameter that you are measuring. That's consistency. So when you think about, measuring, say, a length of a human, then what do? You take, say, 50 people or 100 people or 1,000 people, measure their lengths and make an average. And you know that sample average is a great example of consistent estimator. So if you take a sample average of n variables and divided by n, then it will converge to expectation x in, well, it will converge actually almost surely, but let's even say in probability, whatnot, the way Bernoulli wrote it anyway. But important is that it will actually converge to the correct average length. So if we assume that our length of the people is generated from normal distribution with some hidden average, then we know by the law of large numbers this sample average will converge to the value we want, to the right value. So now, if you look at this one, and of course this is not something that physics people want to see, but if you look at it as a mathematician, I say it is not a very difficult formula, but it is some sort of abracadabra in the sense that I really do not know what happens when my graph grows. I do not know what happens when I let n go to infinity. Will it so my sample becomes bigger, will it converge somewhere, and if yes, then where, and things like that. And there, you already can become a little bit suspicious about this variance. So this is what we wanted to investigate. Yeah, in particular, you see that you don't see big disassortativity in large networks. So then you may think, what is the reason? Are they really never disassortative, or this is just a faulty way of measuring it? Okay, so to do it, we want to rewrite this thing. So the writing was not very convenient. We want to rewrite it, and we have some elements in this formula. So, for example, this summation, it's very easy to prove that this summation is simply sum of all degrees squared. Why? Because we sum over ages here, and when you sum over ages, then basically, so this guy has degree 5, for example, and when you sum over ages, you sum all these ages, so all 5 ages you sum up, and every time you add a 5, right? So this 5 you will be adding 5 times when summing over each age. That's why square appears. Okay, so this summation will very easy to check that it's sum of squares, and similarly this summation is sum of third powers. Hey, third power is never very good news, especially when you have heavy-tailed degrees, but that I'm coming back a little bit later. So when you rewrite it this way, then my whole formula can be rewritten like this. That you have to simply believe me that it's correct. You can check it with pen and paper. Okay, so this is my formula. And now, what I also know, as some of you already heard today in the lecture, that in real-life networks we have so-called power law degree distribution. And now, what does it mean? So, assume that the degree of a node is just a number of links, and let's denote by pk a fraction of nodes of degree k. Okay, and then power law means that this pk is approximately a constant times times k to some negative power, right? So this is what we call power law. Like what approximately means doesn't even matter now, but that is what is power law. Actually, these power laws are very good model for graphs where degrees have very high variability, so that there is no such thing as a typical degree. That's why they call them scale free. As I mentioned already on the lecture, like if you think about human length, then there is a certain scale. You know that humans usually are around like 150 to 220 centimeters, and sometimes there are outliers, but that's already disease. Most probably some how should I say? I remember this word in Dutch and in Russian, but not in English. But anyway, so something is wrong basically with this person, so humans have typical length. You can be a little bit short, a little bit longer, but there is no such person who can walk on my palm, and there is no such person who will be up to the ceiling here. But in networks there are. So there is this Katy Perry on Twitter, and she had 60 million followers, and I have also a Twitter account, and I have 200. So these are uncomparable numbers, simply. And that's what it means scale-free. So we want a mathematical model that models the scale-free behavior. And this power law is such model because it's very easy to check that this negative power of k decreases quite slow. So even if your k is very large, say 1000, still you will get some numbers here, say, okay, maybe 1 over 100,000, but 1 over 100,000 in a network such as Twitter, which is huge, is not actually a very small group, you know? So, so this reduces slow, so that's why it is a good model for high variability. So this is a formal definition, so we can express this probability that degree is greater than x with this formula where Lx is slowly varying. Formally slowly varying satisfies this definition. Basically, it's very easy to check that definitely constant is slowly varying, but also logarithm is slowly varying. When you substitute logarithm here, what you will see, logarithm t plus logarithm x divided by logarithm t, and t goes to infinity and x is fixed. Then you will get 1 in the limit. Okay, so this is our mathematical model for the degree distribution. And we do know a lot about how realizations of such power laws degrees behave. For example, there is such thing as extreme value theory, and it tells us something about maximum degree. So this is a theorem from extreme value theory, but basically it says that the largest degree, or say largest k degrees, scale as this an, and actually this an is some power of n. So this theorem basically says that if you take degrees and sequence of n degrees for n nodes that follows the power law, and look at your maximum, the biggest one, then this maximum will be quite big. So it will be approximately of that order. And then you may start worrying what will happen if you take this thing to the third power, right? Because remember, in our formula for correlation coefficient, we had this third power in denominator, yeah? And if you take this thing to the third power, you will take 3 over gamma, and actually gamma can be just greater than 1, so it can be actually smaller than 3. So actually that can be quite huge thing, maximum degree put to the third power. And this is where you can start varying a little bit, and maybe you can start varying even more when you realize that when you realize the following thing. That's terrible. I'm sorry, it really hurts my hands. Okay, so so assume that we have this. The probability that degree is k is approximately constant times k to the power minus gamma minus 1, right? Then if you want an expectation of d to the power p, to any power p, then what we are going to have? Then we have to sum, say k from 1 to infinity, right? And then we write here now constant, doesn't count really. Well, you can say approximately as well, doesn't matter, just for understanding, right? Times k to the power p times k to the power minus gamma minus 1, right? And now you see what happens, that this thing can be actually finite only when P is smaller than gamma, right? Because here we have -1, and we know when the series sum up to something finite, the power of k has to be slightly more negative than -1, right? So when gamma is bigger than p, then we have that. But it is actually infinite when p is greater or equal than gamma. And that means that, in fact, you see in our famous formula, if we go a little bit back to it, we were measuring there, sorry, I went forward instead. Yeah, so we were measuring here, even a little bit more back. We were measuring here like the second moment. However, if our gamma is between 1 and 2, then even second moment doesn't exist. So what are we measuring here? What is it? What is this object and where will it go? You know? So you have come up with a brilliant estimator for a parameter which is not defined. I mean, if your variance is infinite, then your rho is not defined even. This measure is only designed for random variables with finite variance, and you cannot just go and apply it to infinite variance, but go and say it to the physicists. When I presented it for the first time, when we didn't yet have this result, so it was some years ago, and this guy in the conference, he said, I said, look, this estimator cannot be consistent because this second moment which is here just doesn't exist. It's infinite, so what's going to happen to your estimator? And he said, Nelly, come on, what are you worried about? Anything can be measured on the data. Which I totally agree. Of course anything can be measured from the data. The question is, which conclusions are you going to make from these measurements? And if you measure something which doesn't exist, then you cannot connect any conclusion to this, possibly, right? So okay, so this is our heavy tail story. So that's basically this is the root of the evil. If our degrees were exponential, then of course all moments would exist, and we would have no problem, and the formula will be fine, and everything will be consistent. Except in real life networks, exponential model is a terrible model because it doesn't capture these huge nodes, right? If it was an exponential model, then Katy Perry on Twitter wouldn't exist. Because in exponential model, if you take exponential to the power minus k here, then and you take, say, if you take exponential to the power minus k, and you take k and you take k equal to 60 million, then this will be a very sad number. Which, I mean, this would never happen in the universe. You know, this is very small probability. So that is basically the problem here. So this n to the power 1 over gamma for a maximum degree is a worrisome phenomenon. And we also have a CLT, and that basically says the same. That is a very interesting feature of the heavy tail distribution, of this regular variant distribution, that actually the maximum rules. So the whole sum will have the same scale as a maximum. So the whole sum of this x to the power p will be scaling as n to the power p over gamma, just as a maximum to the power p. So that is a very big difference again with exponential scenario. When you sum up, say, when your x is normal, say mu sigma square, then sum xi from 1 to n is approximately mu n. Yeah. So and the maximum of these guys is much smaller order than the sum. But unfortunately in this heavy tail scenario this is different, and if p is greater than gamma, then actually the sum can be also even greater than n. And the maximum will contribute the most. Okay, so now what happens with our correlation? So why is it something which is has actually effect on what we observe on the data. So we had our formula, and basically it was cross products minus expectation square divided by variance. Like here, cross product minus expectation square divided by variance. And this part is always non-negative, because we are measuring something about degrees. Variance is in any case never negative, and cross products is cross products of positive random variables. So that is always positive, and the only negative part is this. So we are going to be very brutal, even just low bounded by this negative number, and we denote by rho minus. And now we are going to, so our correlation coefficient in any case can never be bigger than rho minus. Rho minus is absolutely the minimum what it can be. Okay, now let's see how big is what happens to our rho minus. So this is how rho minus is expressed, and here degrees to the power 3. So this guy is going to be very big. So what can we expect to happen to the whole fraction if these guys to the power 3 will become bigger of the order than that guys, which also have some powers, so it's not given that they are big, but if for some values of gamma these guys are bigger than this numerator in the order of magnitude, then the whole thing will vanish. So you will never observe negative correlations. This is what is going on. Now, and well, we make some assumptions, but basically this is corresponding to the assumptions of this heavy tail distribution, and then what we see. Under these assumptions of heavy tail distribution, this is order of magnitude for this term, and this is order of magnitude for that term. And if your gamma is between 1 and 3, as usually the case in real-life networks, then you have to believe me that this order term will be higher. And that's how this denominator will kill the whole fraction in the limit. The whole thing will converge to 0. And it means that with this correlation coefficient, you are never capable of measuring negative correlations. It's simply because of the big size of the network will just kill it. Okay. And this is basically, this was basically our result with Remco van der Hofstad. Then we proved that actually under the assumptions which are natural for these heavy tail distributions, the limit of our correlation coefficient is never negative. Okay, you can also say, so the conclusion is large scale graphs are, large scale free graphs are never disassortative. But that's of course a nonsense. That cannot be true, because whether the graph is assortative or not doesn't depend on whether it's big or not. It is simply how it is designed, the graph, right? We can design a very big graph where big nodes will connect to small nodes. It's possible. It is simply that this measure will never be able to show it. Because after all, this measure is a summary of the whole graph, and this is simply very poor summary. Yeah? So this is what is happening here. We also propose then alternative, which is rank relations, and this is not something that we come up with from on top of our head. It is actually quite well known that you cannot use correlation coefficient when variance is infinite, and for that statistics already knew that this what you have to do. So what we do here, we go over all ages, and what we do here, we look at the degrees at the end of the ages and we rank them. So the highest degree receives rank 1, the second highest receives the rank 2, etc. And then we compute correlations between the ranks instead of the degrees. And sometimes there are ties. For example, when we go over ages of the same node, then always we will see the same degree. So there are a lot of ties. But these ties we are going to resolve at random. So by just adding some uniform random variable to it. So basically we resolve the ties at random. And then we obtain a measure which is called Spearman's law. So we look at the degrees on the two ends of the H, we resolve the ties at random, we introduce the ranks instead of the degrees, and then this is exactly the same correlation coefficient, but for ranks instead of the degrees. Then you can say, how come you have here the number of ages? Well, because what is the average rank? If we have E ages, right, then the average rank is E over 2, right? Well, E plus 1 over, whatever is written here. So E plus 1 over 2. That's the average rank. Yeah. So and this is also because we have all ranks from 1 to E. Then if you compute the variance on this vector, then this is what you will obtain. So these are deterministic, and the only randomness remains in this cross product. Yeah. Okay. So again, the bottom line, instead of using this Pearson's law, we now use Spearman's law, and the Spearman's law is exactly the same thing, only instead of degree we use the ranks. Is that clear? So the whole funny business disappears because the ranks are all between 1 and n. So it's basically like scaled uniform random variable. So it cannot be huge. You know, so the degrees can be very huge. It can be 60 million. So the ranks are uniformly distributed on the interval. Therefore, no funny business. It doesn't even matter whether you have finite variance or you don't. You only just need the distribution. Okay, so yeah, so you see, so these ranks are in fact number of ages times something uniform, and therefore no funny business, no influence of high degrees and everything. So this is actually a classical approach, as I said already in 36. This two statistician says that if your variance is infinite, that you cannot use Pearson, and you have to do rank correlation. But of course, when application arises and everybody jumps on it, then this sort of old wisdom is often forgotten. Okay. So now, we have proved some theorems, and indeed rank correlation is consistent. So rank correlation is consistent. I will skip that. Instead, I will show you how it works and what it does on 3 models. And we start with configuration model, about which some of you today heard at the lecture. And this configuration model is a random variant. So we take a node, we have this degrees, and then the nodes are connected purely at random, no preference. What does it mean, no preference for correlation? What should be the correlation then, if there is no preference? Positive, negative, 0? If we just do everything at random? 0. Right? So if there is no preference, so big guys connect to everybody they like, and small guys also, there is no preference, so it should be 0 correlation, right? This is what we expect. Okay. So, and indeed, we show that both these correlation coefficients converge to 0. So that is no surprise here. And in fact, this Pearson also converges to 0 for 2 reasons. One is because the degree to the third in the numerator kills everything, but another is actually the neutral variant. So here everything is logical. And these are the results for the configuration model. But even already in these results, we can see that rank correlations are a little bit better behaved. So what is here? This is the size of the graph, and these are the values. So for each graph, we did 20 simulations, and we put these points. So for example, this was a graph with 100 nodes, and we made simulations, computed the row, this row, and the Spearman's row, and we put these dots here, and the Pearson, the bad guy, is in blue, and the rank correlation is in red. And what we see that they both go to 0, although rank correlation go to 0 a little bit faster and have slightly smaller spreading, but still you cannot make a very hard case with that. So now we started thinking, okay, so our point is that this Pearson can never go to negative, can never converge to anything negative. Can we create an example of a graph which is clearly disassortative, so all big nodes are connected to small nodes, but still correlation coefficient goes to 0? So, and indeed, we can create such graph very simply. So this is our original graph with these blue points, and what we do, we cut every edge and put an extra node here. So now we have many, many more nodes. But what happens in this graph, that now everybody is connected, everybody in the original graph is connected to a node of degree 2, which is like very small. So this is clearly very disassortative. All big guys are connected only to the nodes of degree 2. Yeah? So this is very disassortative, and let's see what happens. So we could write down this Pearson coefficient. Well, it's a little bit different formula because we have more nodes, because on every edge we have now a new node, so number of edges doubled, number of nodes increased. And we actually can find the rank correlations, and we can find this number. But what happens that the Pearson actually will go to 0 if our second moment of degree is infinite. So better maybe show to the picture. Here is what's happening. Again, graph of size 100, 1,000, 10,000, and 100,000. And this is the Pearson correlation coefficient, so the classical one. And look at that. Although the graph is very disassortative, it goes nicely to 0. However, our measure, which is rank correlation, goes and stays around its theoretical value, and the spreading is very small and goes only smaller. So you see, with rank correlation, we could discover this disassortativity. With classical, we couldn't. It behaved as if variance was neutral, but it's not. Yeah, is it clear? Yeah? Okay. Nice. Now, finally, preferential attachment. You have this result where it should converge the Pearson. And here is again what is happening, that when graph sizes grows, then Pearson goes again to 0. But in this particular realization, the rank correlation was negative and it stayed negative. Of course, you can ask yourself, what does rank correlation measure? Because it's not exactly the same. That's true. But still, we can see that, yeah, here is clearly negative, and it be that all graphs have this neutral variance. Like, for example, we can say rank correlation in this model are negative but smaller than in that model. Here was minus 0.75. Here is minus 0.4, right? So we can reveal something with rank correlation while Pearson just goes to 0 all the time. Okay, so then I also did some results on the data. And here is my most beautiful result. These are very old crawls. These are like 2004 crawls of the World Wide Web. But this is the same domain, UK. But this has 100,000 vertices, and this has 1 million vertices. And it's like the results are too good to be true, because if you look at Pearson, then you clearly see, and it's the same domain, right, that for smaller crawl, it is quite negative, and for larger crawl, it becomes much smaller. And if you look at the rank correlation, then they're almost the same. So the structure remains the same, but because of the size of the graph, Pearson disappeared for a larger graph, but rank correlation persisted for the larger graph. So I hope this was clear. So that is, you know, it's like a little bit like black magic, that you measure something very natural and suddenly it doesn't behave the way you expect. But that is what happens, and that's why you have to do your math very carefully and never use not consistent estimators. I mean, that's obvious for everybody, but it's very clear, very difficult to actually communicate this message to interdisciplinary community. Okay, so now actually it's time for us to finish almost, but I wanted to add a little bit about somewhat new results. So this previous work that I was showing was some years ago that we did with Remco van der Hofstad. But after that, my PhD student, Pim van der Hoorn, was working also on this problem. And last summer, we had an intern from China who was called Don Yao. And Don was extremely hardworking and talented student. And with Don and Pim, we analyzed together another correlation measure. So, to be very honest, these funny features of Pearson is not unknown to the community. People realize that something fishy is going on with Pearson. You have to at least be aware of that. So many people know that. But sometimes people say, okay, if Pearson is not good, let's do some other measure. Let's do average nearest neighbor degree. That's another way to measure it. So average nearest neighbor degree is as follows. So it is for a given degree k. For given degree k, what you do, so provided that such nodes exist of degree k, what you do, you go over all the neighbors of k, which we denote here by k prime. So you go over all degrees of k prime, and basically what you do here, you average over all nodes connected to this node. So basically what you do is, the formula probably is not well clear. So this is the probability that a neighbor has degree k prime, given that our original node has degree k. So what you do actually is, you have, say, 3 neighbors. This one has degree 3. This one has degree 2, and this one has degree 5. All right. So your average nearest neighbor degree here will be 2 plus 3 plus 2 plus 5 divided by 3, whatever the answer is. But your degree is 3, and what you do, so this will be a contribution for this one node, but you look at all nodes of degree 3 and average over them. That's basically the mechanism. Very easy. For every k, what is the average degree of the neighbors of nodes of degree k? Yeah, and then, of course, if the function that we make, so this is a function of k, and if this function is increasing in k, it means the bigger nodes have bigger average neighbor degree, right? So it means assortative network. If it goes down, bigger nodes have small average neighbor degree, disassortative. If it's neutral, should be staying equal, right? Random variance should be more or less constant. So that is what we expect, and this is another way of measuring degree-degree correlation, more informative, because instead of one number, you get a function of k. So it's more informative. Now the question is, does this one behave well? And so this is a little bit different expression does matter. So the question is, does this function behave well? And the answer is no, it doesn't, because it does exactly the same. It is again summing up over neighbors. And actually, I was telling you always about the third powers, but we also have the second powers, and second powers are also not good if your variance is infinite, right? But infinite variance, so you see, if your p is 2, then the second moment exists only for gamma smaller than bigger than 2. But in real life networks, it's often between 1 and 2. So variance is often infinite. So it's not only here that is a problem, but here is also the problem. And this is a problem which is difficult for average nearest neighbor degree. Because when you go and sum up over ages, then you will get the squares, just as here. So denominator there will not be important, but this part will be a problem. So long story short, let me skip that and that. So long story short, when we have finite variance, everything is fine. And our average nearest neighbor degree will converge to deterministic function, and we can see whether this function is increasing or decreasing, and we can do something with it. If it is configuration model, then of course it will converge to a constant. However, if our variance is infinite, then we have a lot of funny business going on. In particular, let's take configuration model. Then we take average nearest neighbor degree. And then actually what happens that this average nearest neighbor degree divided by some positive power of n will converge to some random variable, stable random variable. Doesn't matter what it is even. So basically, your average nearest neighbor degree will scale as a positive power of n, positive because gamma is smaller than 2. This is a difficult case when gamma is smaller than 2. So when gamma is smaller than 2, this is a positive power of n. So your average nearest neighbor degree will increase with n. Moreover, it will also have random fluctuations. And that is what the result actually says. And indeed, and we also can average nearest neighbor rank is our solution, but let me show you the pictures. So this is what is happening. So this is our average nearest neighbor. Don't pay attention that it's decreasing. It's decreasing for different reasons. It's decreasing because if you generate 100 networks, then in not all of them will have a node of degree, say 150, and that's why it goes down. But don't mind it going down. Just look about where it is. So when our variance is finite, then it is all similar level. It just goes down for the different reasons, and fluctuations are not big. But when our gamma is smaller than 2, so variance is infinite, just see what happens. It's not even a plot. It's like a horror plot. I mean, come on. That is completely uninformative. And look, so the color denotes different values of n. So when n increases, you see, n increases, it becomes bigger and bigger and bigger because it scales as a positive power of n, so it becomes bigger, and it fluctuates wildly because of the random factor that it has. So that is not, by no means, it's a good measure either. It's just hidden, the difficulties are just hidden in it. So this is the results that we did, and look how the nearest neighbor rank behaves. Of course, here I'm cheating a little bit because the slope, we know exactly what the slope is, and here we made a correction for the slope. So slope was there, but we made a correction for it. But we know exactly what correction is. But here, even if you make a correction and get rid of the slope, the plot will be even more unreadable because fluctuation will become even higher. Because we will basically put it up, and then these little fluctuations will also blow up. That's what will happen. But this one is really beautiful. And notice that even when variance is infinite, we have some deviations. This is as a function of k. So this is k, and this is average nearest neighbor degree, average over 100 realizations. So when variance is infinite, it has slightly higher fluctuations than here, but still it's very nicely around its theoretical value. So that is, again, a much better measure. Of course, interpretation of rank relations is another question, but at least it definitely works better than that, right? Yeah, so that's all I wanted to tell you today, and thank you very much for coming so late in the evening and attention. Yes, questions?
No questions.
It's totally clear.
Yeah, no, that I don't buy. I have been working in university for 20 years, and I know if there is no question, it is either it is completely unclear or everybody wants to go home. But it cannot be that everything was completely clear. If everything was completely clear, then you can have question what's happening next, for example. But okay, accept if you want to go home.
Mathematical techniques of proving these theorems.
That's actually a very good question. So it depends very much on the model, but in the configuration model, usually what happens that it is a lot of hassle. So what we are doing, for example, for average nearest neighbor degree, For example, here we take this expression which we have written. We have it written explicitly. This is a joint distribution of the neighbors. So it's written explicitly, and then what we do, we split it in parts. So say in the main part we can bound everything the way we want, and in the other part where it is beyond our boundaries, but our boundaries are chosen in a special way, in such a way that you very rarely go beyond the boundaries. So, and then what happens that within the boundaries we can bound everything and show that, for example, we can show, for example, that this difference goes to 0, not boundaries for k. This is for each k. We bound the terms that constitute this difference, and then for the main part we can show that it goes to 0 because of the boundaries that we have, and whatever happens outside of boundaries goes to 0 because it happens very rarely, because there are very few terms there. So, and this is the bottom line of the whole technique for average nearest neighbor degree. For the Pearson, because there was somewhat different, but actually in the lecture today I made assumptions about the model, configuration model. So you make certain regularity assumptions. For example, you can assume that this joint empirical distribution of degrees onto n's, you have to assume, I skip this technicality, but you have to assume that it goes to some limit. And then what happens for Pearson, because it's only one expression, and we didn't want to go into so much detail, we just proved convergence. So there you do also, you split in different terms, and under your assumptions, terms go where they should go. That's more or less the technique of all these proofs. In configuration model, you also use a lot the construction that they are connected at random. So there you also use. Very good question. Thank you. Yes? No more questions? Thanks a lot.
Thank you.